Okay, so that leads us into some things I want to talk about. I am going to talk about evaluation measures for a bit today. So, it's going to be like a little bit of a hodgepodge class. Okay, I am going to talk about a few things which do not really fit into a bigger theme, right. So, for as far as evaluation is concerned, we have spoken about some very standard things so far, right. So, in classification we talk about come on, give me something, yeah. What would be the evaluation measure in classification?
Misclassification.
Huh? Misclassification error, then
Cross entropy.
huh?
Cross entropy.
Cross entropy, then
Gini
Gini index. Okay, Gini index is not an evaluation measure, right. Gini index is more of a parameter selection mechanism, right. Right. I can after I finish the classification I can actually compute some kind of a deviance, right, and I can say okay, this method giving me a better deviance than that method and things like that, or same thing for 0-1 error. I can use squared error, right, squared error of your thing to a target variable, and anything else can I use?
Penalties.
Huh?
Penalties.
Penalties in what sense?
In the SVM
Aha.
and the last one.
Okay, so there are a couple of things that we have to be careful about here. So there is something which I optimize, right, to get to what I want, right, and there is something which I use for evaluating what I finally get. Right. If you limit ourselves to the supervised learning scenario, right, we have not even started unsupervised learning. Limit ourselves to supervised learning scenario. More often than not, what we really want to evaluate ourselves with is the performance on the entire data distribution, right. So, I have some distribution of data, right, I do not know the distribution a priori. Right. Remember, go back to the very first class, we started talking about something serious, I mean not the one with the pictures, right, the one with the Greek in it, right. So, in that class we talked about there being an underlying data distribution, right, and that we did not know about this data distribution. The only way we know anything about this data distribution is through training data points, right, is through the samples that are given to us, right. So, there is an underlying right. So, we had this distribution. So, what I am really interested in is finding out when you give me a classifier how well it is performing with respect to this distribution, right. So, in that sense how well it is performing, I am not really interested in figuring out the square, the ridge regression loss or anything like that, right. So, I am using that to come up with a single classifier, but at the end of the day when I am looking at how well this classifier is performing with respect to the underlying distribution, I have certain measures. So, one of them is the 0-1 loss, right. So, I do not care how we arrived at the classifier, right, I just want to look at the 0-1 loss and then I can do that, right, that 0-1 loss gives me the misclassification error, right. So, ideally that is the evaluation measure that you should be using, okay. So, sometimes what people do, because they are optimizing a different objective function, they choose slightly different evaluation measures that can make their method look better, right. So, squared error could be one evaluation measure. If you are doing classification, 0-1 loss is the measure that you should be looking at. If you are doing regression, a little tricky, but squared error is the most widely accepted measure for looking at regression, but then you can look at other things also like deviance and other things, you can use that for classification, right. But having said that, how do I estimate it is easier for me to write classifier or I will pick one, I am going to pick classifier, but some of what I talk about now it works for regression as well, right. How do I estimate the true performance of the classifier? So what do I mean by that? I have given you a sample data, right? I have given you some sample drawn from PXY, right? So based on the training that that's all the information I have, right? And I can use some of the data for training. Right? I actually find the parameters. Now how do I find out how good these parameters are, or how good is my, there are two questions to ask, right? So the first question is how good are my parameters that I have found, okay? The second question to ask is how good is the method that I use for finding the parameters is. If you give me a slightly different data, will I perform better or worse, right? How will I perform, right? So I need to know something about the technique, right? Suppose I am proposing a new technique, right, and I want you to go use it on your data later on, right? But I should convince you that you can use it on whatever data you have, right? So that means I will have to convince you that my technique is good for finding the parameters. This is the two things here. For a given set of parameters, I have to figure out how good they are, right? And I also need to tell you how good my overall mechanism for finding these parameters are, right? So for a given set of parameters, how do you find out how good they are? On the training data, is that good enough? On the testing data, cross validated. Okay, so people get, so we will get to this thing, right? So one thing which we spoke about earlier was to split the data into train and test, right? So if I estimate parameters on the training data, okay, and run it on the test data, that will give you some performance, okay. Is that a good estimate of the true performance of the classifier? Why not? So test data might not be independent of the training data. Okay, the training data may be biased. I might have overfit the model.
Taken out all the training data and test data from a particular section of the organization.
Then you are doomed. Right. So no, that's actually a very valid point. In fact, that is something which you will face in real life, right? But the assumption mostly we make in theory is that the training data that is given to you is a sufficiently representative data of the true distribution. Okay, if that is not the case, then you are doomed anyway, right? So you assume that it is the so in real life that happens, what do you do? In real life that happens, okay, I mean you can't avoid it, you can't just say okay, I am assuming it is a properly representative sample of the underlying distribution, then what do you do in that case?
Stratified sample.
Come on, he is telling that you are not sampled the entire range of PXY, so what is, exactly, so figure out where you are deficient, right? So sometimes the most obvious thing is what you have to do, you have to sample more, right? But then do not blindly sample. I mean, of course, if you blindly sample, you might actually return the same samples from whatever region you already have, right? So what you should do is you should be more careful in how you do the sampling. So you can use, this is where you try to understand what the data is all about, right? So you try to understand how the data is distributed, the data that is given to you is distributed, and figure out if there are parts of the input space which you believe are important but are not covered in the data, right? Go and try to sample from that region, right? So there are different names for this, okay. So one popular thing that people call this by is called active learning, because I actively am asking you for samples, okay. So I am not passively learning from the samples that were given to me, okay. The learning algorithm comes back and says, hey, I want to know more about this part of the state space, give me some samples from there, right. I want to know more about this part of the input space, give me. So these are called active learning methods. So your question is valid. Point of this discussion is, yeah, one train, one test is usually not a good idea, right. So what do you do? There are two things which you can do. You can try to get multiple training sets from their data, right. You can try to get multiple training sets from the data, right, and try to Nobody is asking me the obvious question. Why are you getting multiple training sets from the data? Why not one large training set?
Might be from 3 to 4, 5 different people.
Huh?
Might be different people sampling the thing.
Yeah, but then why not pool everything together and then create one large training set?
Minimize error at every stage.
Minimize the data every stage.
The variation might be large.
Yeah. Close.
Weak classifiers.
Huh?
Weak classifiers.
Yeah. So I will have to spend a whole week on weak classifiers, right? So we'll come to that, right? So it's a see that's one very amazing property that we'll look at later. Which probably in the next class. I mean, later means pretty soon. On how you can take a lot of not so good classifiers, right? Which are just better than random. Of course, it has to be better than random, right? It can't be worse than random. So classifiers that are just better than random, that give you an accuracy of 51%. Okay. So in the 2-class problem, that is just better than random. Okay. I can take classifiers that give you an accuracy of 51% and I can produce arbitrarily powerful classifiers. Okay. It's an amazing insight that came about a couple of a decade and a half ago. No, maybe no, I am old. Yeah, more than 2 decades ago, right? And it won the Gödel Prize and things like that. It's an amazingly wonderful insight, and we'll talk about that, right? So that completely revolutionized machine learning once, right? People then started saying that, oh, I really don't have to build this super optimized classifier. I can build a lot of this almost moronic classifiers, but the operational word is almost, right? And I have a lot of them, right? I have a lot of them, and I will be able to do really well. In fact, in many applications that we have worked on, right, in real life, where I have worked on with real data, I find it very hard to beat these kinds of classifiers. Right? You can think of whatever optimal classifier you want to come up with, right? But beating these kind of groups of weak classifiers is actually very hard in practice. Right? So we'll talk about that. But no, that's not what I meant here. I still have a point I'm trying to make, right? So yeah. So even if you do one large training set, if you do train one large test set, right? You can get away with it provided large is large enough, right? So provided large is something that is dense in your input space, right? If the large is so large that you essentially plaster your entire input space, right? So any point in the input space, if I pick, there will be one point very close by in the training set. That is what we mean by dense. I mean there is an actual more mathematical characterization of dense, but if my training data is really dense in the input space, then it is fine, right? Then I can get away with just doing one sample, right? One very large sample. But usually what is going to happen is you are not going to get such a large sample, right? So you are going to get a much smaller sample than that, and therefore if you just use one sample and try to make an estimate, okay, then the variance, do people remember what is the variance of the estimate? We talked about this again.
Small change in the input data, there is a significant change in the predicted result.
No, that is unstable. I am talking about variance. Yeah. Huh? Sorry?
A lot of models. You train a lot of models.
On data of similar size. If I train a lot of models on data of similar size, the parameter estimation I am going to make will be varying a lot, right? So it turns out that instead of doing one sample and then trying to train this, okay, if I take many samples, right, and then find the parameters on these samples individually, right, and then take an average of those, okay, turns out I can show that the variance will be lower in that case. So what is the variance you are talking about? The variance in the parameter that we are estimating, okay, and what is the parameter we are talking about estimating here? So here is the point where I am going to confuse all of you, but the parameter I am talking about estimating here is the error, is the misclassification error, right. So I have the classifier, right. What I am trying to measure is the misclassification error, right. That is what the whole discussion was all about. I am trying to estimate the misclassification error, right. So what I do is I start off with many samples of data, right, and on each sample I train a classifier separately, okay, and then I look at how the performance is on the test data, and then take an average of all these performances, and then I can tell you, okay, if you give me a new set of data, I expect to make this much error on the test data, right. I am trying to figure out what the performance of the algorithm would be on a unseen train data, right. See, if I remember I was telling you I want to know how good my algorithm is, right. So this way I can estimate the performance of the algorithm on the unseen data, right. So there are many ways in which you can generate this there are many ways in which you can build this multiple training data sets, right. So many of these are have strong roots in statistics and were typically designed in eras where the amount of data available to you was small, right, and the amount of data available was small, and we were trying to see how you can fake multiple data sets with a small amount of data, okay. So the first technique is known as bootstrap, okay. So bootstrap is actually a very powerful statistical technique. It is used in a variety of different places. We will come back to another use of bootstrap a little later.